Hi everyone, in this video what I'd like us to do is to practice applying some of our additions to alkenes that we've learned in class. And so in doing this, what we're going to do is we're going to go step by step through how I would solve problem 9.50, so 950, in the textbook. And so what we've got is we've got this alkene shown here, and in this first section of the problem, what we notice is we're first treating the alkene with boron THF followed by a basic mixture of hydrogen peroxide. And so what I want you to first recognize is the fact that this is a hydroboration oxidation, and I'll just abbreviate that by HBOX. So this is an example of an anti-Markovnikov hydration of an alkene. So we'll abbreviate that as anti-Mark. And so the way in which I like to go about predicting my products is realizing the fact that we're not breaking any sigma bonds in this reaction, but rather we're simply functionalizing the double bond of the alkene. So I like to first draw out the sigma bond framework of my initial alkene. And so what we're going to do is we're going to add something to each side of this alkene, which I'm going to denote with two little dots there. And to do that, then we're going to look at our product shown here and realize that what we're adding in hydroboration oxidation is we're adding an equivalent of water across the double bond. And so because this is an anti-Markovnikov hydration of an alkene, we have to realize that we're adding our proton in this respect to the side of our alkene that is the most substituted because it's anti-Markovnikov. So what I'm going to do is I'm going to go ahead and add our proton in here. So the reason I'm adding this to this side is this is the more substituted side of our former alkene. It has two groups off of it versus the other side, which only has one carbon-containing group. On the other side, however, we're going to wind up adding the OH, the hydroxyl part of our water. And what this is going to do is this is going to give us our product alcohol. And so really the question now we have to ask is, what are the stereochemical implications of this problem? We realize that hydroboration oxidation indicates the fact that we are going to have to add our proton and our hydroxyl group to the same side of our alkene. Interestingly enough, though, what we notice is that this center here is not a chiral center, namely for the fact that this side bound to this this sp3 carbon is exactly the same as it is with this side, so we don't really need to be concerned about the stereochemistry there. However, we notice at the alcohol part of our product here is indeed a chiral center in the fact that we do have four different things bound to this sp3 hybrid carbon. And for the fact that this boron THF can approach both sides of our starting alkene, we have to realize that we are going to make both enantiomers of our product relative to the stereochemistry at the center of the hydroxyl. And so what I'm going to do is I'm just going to draw out both enantiomers of our final product, and really the difference here is with the direction in which our hydroxyl group is shown here. And so in this case, because we're only forming one new stereocenter, we are going to form a pair of enantiomers. So in our second problem here, we're going to take our same starting alkene and we're going to add an equivalent of bromine to that alkene. So this is an example of an anti-addition of X2 across a double bond. And so again, I like to approach the problem in the same type of way. First, draw out our sigma bond framework to our product. In this case, it's going to be an alkyl dibromide. And then in doing that, what we're going to do is we're going to add the bromines to both sides of our alkene. Okay? And so again, what we have to realize is we're not making two different we're not creating two different stereocenters in this respect, namely for the fact that this sp3 carbon, which was initially part of the alkene, is not chiral. Again, just like we showed above, this appendage is exactly the same as that appendage, and as such, this is not a chiral center. However, our bromine here is indeed a chiral center. And so what we're going to do is we're going to show both ways that our bromine can add. and I'll draw on the hydrogen here just for clarity, we can see that we are going to create, again, a pair of enantiomeric compounds. And so finally, what I'd like to show you in this short video of functionalizing this alkene is the addition of hydrogen gas to our alkene in the presence of a platinum catalyst. And so this is platinum that has been deposited upon activated charcoal. And so what this is going to do is it's simply going to add H2 across our bond, creating an alkane, so a fully saturated hydrocarbon from what was initially our alkene. And so let's go ahead and do that. Again, just draw out our sigma framework, because remember, we're not breaking any sigma bonds. What we're simply doing is we're adding things to what was initially our alkene. So what I'm going to do is I'm going to add hydrogens to both sides of where our initial alkene was, generating our hydrocarbon. And so in this respect, we're not generating any new chiral centers, and so we don't really have to be concerned about whether we're going to produce pairs of enantiomers in our product compound. And just for clarity, the reason why we know we're not producing any enantiomers is the fact that you can see here, again, for the reasons we showed above, this is not a chiral center right here. And then on the adjacent carbon, we have two of the exact same substituents. They're both protons there, indicating the fact that this is also not a chiral center. So again, as a reminder, catalytic hydrogenation simply takes what was initially an alkene and hydrogenates that by adding hydrogen across the double bond to produce an alkane product. And actually, we've got a little bit more time here, so what I'm going to do is I'm just going to scooch the paper down. And let's do one more addition to this alkene. In this case, we have an addition of HBr across the double bond. And so what I want you to think about is when we're adding HX across a double bond, while there are a few exceptions, this is an example of a Markov-Nikov addition. And so in doing that, what we're going to want to do is we're going to want to follow Markov-Nikov's rule in determining our product. And so Markov-Nikov's rule simply says that we're going to add our proton of HBr to the side of the alkene that is less substituted, thereby giving us the more stable carbocation. So let's go ahead and do that. I'll show the mechanism out for this one, because I think drawing the mechanism is important when determining the products of some of these types of reactions. So what this is going to do is this is going to add a proton to the one side of our initial alkene, but on the other carbon, it initially had 4 bonds, but now it only has 3 because its double bond has been broken. This carbocation then is then going to be able to be reacted with our halide anion, which was spit out when HBr was nucleophilically attacked. That being said, a question we have to ask ourselves first is, okay, this tertiary carbocation, is there any kind of rearrangements that can happen to make it more stable? And in reality, because it's already a tertiary carbocation, unless we were going to make a benzylic carbocation, the answer really is no. So to finish this up, we can have our bromine nucleophilically attack at our carbocation center, generating our new alkyl bromide product, shown here. Let me just scooch that over. And so again, when thinking about stereochemistry here, we're not actually generating any new chiral centers, and so this is an achiral molecule, and you don't necessarily need to specify whether this product is forming a pair of enantiomers or not. Okay, I hope that this clarifies a little bit how to approach some additions to alkenes. If you have any questions, as always, stop by my office, or if you have any ideas for videos, please let me know. Okay, till next time.